Okay, so this kid named Scott called the girl named Sally a very, very bad name in pre-K school. So the teacher puts him in the timeout box. The box is all enclosed, but knowing that the kid needs to breathe, she cuts out a square on the box a feet higher than Scott's height. As much as he tries, Scott can't get out of the box because the box here imposes a potential barrier on him. Unless he hasn't skipped leg day, he can't possibly come out. However, there is a very small chance that he could. In classical physics, if Scott's energy of his jump is greater than the potential energy of where the square is, then he can leave the box. But if Scott's energy of his jump is less than the potential energy of where the square is, then he can't come out. Or is that what people want you to think? But let's say Scott, a normal kid in pre-K, was actually Ant-Man and shrunk to the size of a subatomic particle. Then believe it or not, he could overcome this potential barrier imposed by the box and come out to the other side. This is called quantum tunneling. In order to understand how this works, we have to understand the basics of how the quantum world works. Quantum physics is a branch of physics that is created to describe all of the bizarre behaviors of subatomic particles like protons and electrons. In this field of study, particles are modeled as wave functions, meaning that particles have wavelengths. In fact, outside of the quantum world, all matter have wavelengths. Even you. This was discovered back in 1923 when a brilliant French physicist named Louis de Broglie thought, since light has particle and wave-like behaviors, why can't particles too? He came up with the de Broglie hypothesis, which states that all matter exhibits wave-particle duality and have wavelengths. He modeled this phenomenon as lambda equals h divided by p, where lambda is the de Broglie wavelength, h is the Planck's constant, which is approximately 6.626 times 10 to the negative 34 joules times second, and p is the momentum of the particle. Since p is equal to mass times velocity, we can substitute it into the equation to get lambda is equal to h divided by mv. Since mass is in the denominator, we know that it is inversely proportionate to lambda. So as the mass of the particle increases, lambda decreases and vice versa. Because we are able to model particles as wave functions and that their wavelengths are actually noticeable unlike humans, we can apply the Schrodinger's equation, which allows us to calculate the wave function. Another scientist named Max Born suggested that the probability of where a particle is can be calculated from squaring the magnitude of the wave function at that location. So by using the equation, you can see that on the left side of the potential barrier, the amplitude is large. This means that in the quantum world, Scott is most likely there. However, the probability decreases as it goes through the barrier. On the right side, you can see that the amplitude is greatly decreased, which means that Scott is less likely, but not impossible, to be on the right side. If the potential barrier is thinner, meaning that if the cutout square on the timeout box is lowered a bit more, then the amplitude of the wave would be a bit larger on the right side. This way, Scott's probability of coming out of the box would be greater. Keep in mind that in classical physics, Scott is basically trapped in the box, but in quantum physics, not so much.